Let's look at another change of variables problem. In this particular case, we're looking to compute the following integral here. We have the integral over the region R of 4 times x plus y times the exponential e to the x minus y integrated over the area element. Now, R in this case looks like half of a square, and you can do this problem several different ways. I often write this up in my notes, but I thought I would exercise the same technique I've done before with a little bit of a twist to it. So you're thinking that when we come up with a transformation that the x plus y and the x minus y will be taken care of, and that's really how this problem is set up. So when you go over to R, you look at these two segments here. This one's very simple, so we're really interested in these two. So notice this particular segment here has a slope of -1, and it's just the line y equal -x. So that's easy to write. And then we transpose and we have x plus y equals 0. Same thing over here. We've just got the line with slope 1 and basically x equal y. So this is just y equal x. So I transpose this and I have x minus y equals 0. So of course nothing about this is unique, and you can write these however you like. I mean, you could do y minus x equals 0. You'll still get the same answer. But now I'm thinking, okay, this is looking really good. I'm going to make an assignment to a transformation. So I'm going to define t from R into S such that u is equal to x plus y here, and b is equal to x minus y. And then I'm thinking, okay, well, I don't want to do a whole lot of work here, so let me just see what this transformation does to these vertices, and then I'll know, because we have a linear transformation, that these segments will all be mapped into segments. So I look at 0, 0, that's clearly 0, 0. And then if we look at -1, 1, just using this formula here, the x coordinate and the y zero out, and then of course we're left with a -2, and then t of 1, 1 is 2, 0. So we get 3 coordinates that we can easily plot. 0, 0 right here, 2, 0 here, and 0, -2 here. So this region is not as simple as some of the regions we've had before, but when you compare this to this, this is much easier, much easier. Now, the only thing we need to do, you're thinking, well, we'll just do a translation of coordinates, but we don't even have to do that this time because this is very simple. Again, this segment here has a slope of 1 if you just do rise over run. And if you just utilize the slope in this point, we get v is equal to u minus 2. So now what we see is that u is equal to v plus 2, and that's going to help us with our limits. So if we think of defining a region in terms of its algebra, we can see that the v coordinate will run from -2 to 0, and if we look at the u coordinate here, it's going to run from 0 to v plus 2. So what we see here is that we still have a more complicated S than we've had in the past, but it's still much more manageable than that, and it's really going to make our integrand much simpler. So this defines the S by our simple analysis here. So now what we can do is go ahead and do the Jacobian for this transformation. It's all set up. So we'll do, again, we've got u and v as functions of x and y. So we're going to do some x partials, we get 1, 1. And then we'll do the y partials, we get 1 minus 1. So we have this. When we do the determinant, we get the -2. But this is the Jacobian that we need for the theorem. And so we know that these are just reciprocals. So this Jacobian of the xy coordinates is just the reciprocal of -2, which is -1/2. So again, a very big time saver using the relationship between these two Jacobians. And so of course I was lazy, I just called this I. So now we need to use change of variables. So we want to transform this integral over R to an integral over S. And so now we've got our nice limits of integration, negative 2 to 0, and 0 to b plus 2 here. And then, of course, the x plus y is just our u, which we have here. And then the x minus y is just our v, which we have here. So that simplifies tremendously. And then, of course, we have the absolute value of the Jacobian and then the du dv. So now what we're going to see is that, of course, we just have a 4 over 2, so that gives us a 2. And then if we look here, we want to integrate with respect to u, so that'll give us a u squared over 2. And now, of course, the 2's will absorb. We have our limits 0 to v over 2, or v plus 2. And note here, when we replace the u with 0, we just zero out the integrand, so we're not worried about that. But if we replace u with v plus 2, we get the square of v plus 2, which is v squared plus 4v plus v. And of course we have the e to the v hanging out because it's constant relative to the u variable. And now, of course, this is just a nice integration by parts, very simple, because this polynomial differentiates to 0. So as I've done before, we just set this up in a table so it's easy to figure out the terms. We will integrate the e to the v, and that's just the same thing each time, so that's really simple. And then, of course, when we differentiate the polynomial, this first differentiation is 2v plus 4, then we get 2, then we zero out. And then, of course, by the integration by parts theorem, we have the alternation in sign. So you can see that this is negative, and these two terms are all positive, so you can even add it up right here. We get the v squared term, and notice we get the 4v minus the 2v, leaving us a 2v. And then, of course, we have 4 minus 4 plus a 2, which is a 2. So the antiderivative is pretty simple when we set it up in the table. And now all we have to do is evaluate using the fundamental theorem of calculus. When we substitute 0 for v, these two terms zero out, but we're left with the 2. And of course, e to the 0 is 1, so we've got that term. And then when we substitute the negative 2, we get e to the negative 2. And then, of course, here we'll just get a 4 plus a, a 4 minus a 4, which I've written here, and then the 2, which is just hanging out. And so now this will just give us a 2 times the e to the negative 2 with a negative sign. So if you want to make it look nice, you can just retire the negative and write this as 2 over e squared. And then, of course, e to the 0 times 2 is 2. And so our final answer is 2 minus 2 divided by e squared. And we are done.